Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar by clicking on the question mark in the WebEx toolbar. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. You will receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, John. Today's speaker is Xin Zhou, Assistant Professor in the Department of Biostatistics at the Yale School of Public Health. Prior to arriving at Yale, Dr. Zhou was a postdoctoral fellow in the departments of biostatistics and epidemiology at the Harvard T.H. Chan School of Public Health. His research focuses on cluster randomized trials, measurement error correction, and statistical and machine learning methods in precision medicine. It's my pleasure to welcome Dr. Zhou.
Okay, thanks for the invitation and the kind introduction. Today, I will talk about power calculation for step-wedge design with binary outcomes. I'm also affiliated with the Center for Methods in Implementation and Prevention Science. There are 4 faculty members in our biostatistics team. The talk actually covers the work of Donna, me, and Fan. Okay, this is the outline of my talk. First, I'll briefly introduce the step-wedge design and the power calculation method proposed by Hudson and Hughes. Their normal approximation method is often used for binary outcomes. Actually, I will show this method is inaccurate. For analyzing step-wedge studies, the mixed effect model and the generalized estimating equations are 2 often used methods. In this talk, I'll introduce 2 power calculation methods based on mixed effect model and based on generalized estimating equations. The first one was derived by our group, and the second was derived by Dr. Fan Li. And since now Dr. Fan Li and I are in the same center, we work together to develop software packages to implement these 2 methods. And the last part is to show how to use the software. Let's start with a motivating example. During the year following the birth of a child, 40% of women are estimated to have an unmet need for contraception. Postpartum intrauterine device, for short, PPIOD, means women's need for contraceptive protection following childbirth. It has long-term protection, is reversible, is safe, effective, and convenient. It also doesn't interfere with breastfeeding. Although this advantage of PPIOD, the uptake is still low, since PPIOD insertion should be performed by a trained provider, and also the services are not widely available. Institutionalized PPIOD intervention can be used to increase the uptake of PPIOD. The new intervention is a routine part of antenatal counseling and also as a part of delivery room services. We want to evaluate the performance of the new intervention. We all know that in clinical research and in pharmaceutical industry, the gold standard is the individual randomized trial, where individual participants are randomly assigned to either the intervention arm or the control arm. However, in practice, some interventions have to apply at a cluster level. Here, cluster means a group of people, such as a school, a hospital, or a household. And the PPIOD intervention I just introduced before have to apply at a hospital level. And cluster randomized trial randomize clusters rather than individuals. An advantage of cluster randomized trial is to minimize treatment contamination. People from the same cluster may share similar characteristics, so this correlation needs to be considered in the design and analysis of a cluster randomized trial. There are three main types of cluster randomized trial: parallel design, crossover design, and step-wedge design. In a parallel design, at the start of the trial, half the cluster are randomly assigned to either the control or the intervention. Another type is a crossover design, where each cluster receives both the intervention and the control. We are particularly interested in the step-wedge design. The step-wedge design is a special case of crossover design, and the crossover is only from one direction, that is from the control to the intervention. The design begins with all clusters assigned to the control. Then randomize cluster at pre-specified time steps called periods, switching from control to the intervention. And the design ends with all clusters assigned to the intervention. In this example, there are 5 periods and 8 clusters. Each row represents a cluster, and each column represents a period. And in this example, starting from the second period, 2 clusters randomized to the intervention at each period. I also want to clarify 2 types of step-wedge designs: cross-sectional design and cohort design. In a cross-sectional design, only one measurement of the outcome is taken per individual, and new individual enroll at each new period. Well, in a cohort design, individual enroll at the beginning of the trial and have repeated measurements of the outcome taken over different periods. So keep in mind that in cross-sectional design, the individual from different periods are different, but in the cohort design, the individual from different periods are actually the same group of people. The step-wedge design is becoming popular nowadays because first, by the end of the trial, all clusters receive the intervention, eliminating the ethical concerns related to withholding potential better treatment. And the second, the step-wedge design is quite useful when it's difficult to implement intervention simultaneously at many clusters. Let's back to the PPIOD example. The study was to investigate the impact of PPIOD use in Tanzania. And this study used the step-wedge design. And the outcome in this study is binary. And the outcome is the unintended pregnancy. It's a binary variable. And in this study design, we want to make sure there's adequate power to detect the effectiveness of PPIOD in preventing unintended pregnancy for 1.5 years following the index birth. And the figure here shows the design in the study. The enrollment was 1 year long, and there are 6 hospitals at 6 clusters, and there are 4 periods. Each time period is 3 months long for enrollment, and approximately 900 women join each hospital in 3 months. So the cluster size is about 900 times 4, that is 3,600. And the total sample size is 3,600 times 6, since there are 6 clusters. And the total sample size is over 20,000. So this was a very large study. And we will come back later to this study for our real data example. Now, statistical power is an important consideration when designing clinical trials. It's closely related to sample size calculation. The power of a statistical test is the probability that it will reject a false null hypothesis. And Hudson and Hughes first derived a power calculation method for step-wedge design with continuous outcome. Some study with binary outcome, including the PPIOD study, also use this method for power calculation. They apply a linear mixed model for a continuous outcome. Let's take a look at this design with I clusters and J periods. Suppose there are K individual at each period from every cluster, and Yijk is the outcome, and Xij is the treatment assignment. Mu is the expected outcome at baseline, and beta is the treatment effect. Gamma J is the time effect corresponding to period J, and epsilon ijk is the error term. It follows normal distribution with variance sigma e square, and Bi is a random effect for cluster I. It also follows a normal distribution with variance tau square. According to this model, any individual from the same cluster are correlated, and any individual from different clusters are independent. The parameter of interest is beta, and we want to test if there exists a treatment effect. The power calculation is based on a wall test for H null. Beta is 0 versus H alternative. Beta is beta A. The power can be calculated by this formula. Here, phi is the CDF of a standard normal, and Z here is the quantile of the standard normal. And the estimated treatment effect of beta high can be obtained from a weighted least square method. And accordingly, the variance of beta high can be computed by a closed form formula. Yeah, this is a closed form the closed form formula for variance of beta high. When we have this variance, we can use the power calculation on the previous slide. Just use this formula to calculate the power. Okay, the advantage of Hudson-Hughes method is that there is a closed form formula for power calculation, so it's simple and fast. The limitation is that this method was designed for continuous variable and not for binary. This method was designed for continuous outcome and not for binary outcome. However, there is some software available to calculate power for binary outcome based on normal approximation of this Hudson-Hughes method. Dr. Hughes developed an Excel spreadsheet for power calculation with binary outcome. And he used this one to approximate the sigma e square. Here, P1 is the prevalence of the outcome in the control arm, and P2 is the prevalence of the outcome in the intervention arm. And he just used the average of the average prevalence to approximate the sigma e square. And also in PASS, PASS is a commercial sample size calculation software, and the PASS provides several options listed here. And however, the normal approximation for a binary outcome is not accurate according to our work. Our work published here. We point out that this method may over or underestimate the power. I use a toy example to show that. Suppose there are 24 clusters and a 3 time period. The P1 is 50% and the P2 is 40%. The ICC is 0.1, and we change K. K is the number of individuals at each period from every cluster. And when we change K and we plot the power calculated by our maximum likelihood method, and also plot the power calculated by Hudson-Hughes normal approximation method, that we can see here the Hudson and Hughes method actually underestimates the power. And to achieve 80% power, the Hudson-Hughes method needs 20% more subject. It's kind of waste of money and resources. Now I introduce our maximum likelihood approach. We consider a 2-arm trial, and the outcome is binary. Including a time effect is a hallmark of a step-wedge design. However, as mentioned in a recent review paper, about half of the study using step-wedge design didn't consider the time effect for the data analysis. So in this work, we consider 2 cases, one with time effects and one without. For the case with time effects, we apply a generalized linear mixed model for binary outcome. The notation is similar to a Hudson-Hughes model. Pijk is the probability of Yijk being 1 given treatment assignment Xijk and the random effect Bi. Here, G is the link function. If the link function is identity link, the parameter of interest beta is the risk difference. And if the link function is log link, the parameter of interest is the risk ratio, or in other words, relative risk. If the link function is logic link, the parameter of interest is odds ratio. In the paper, we consider the identity link, and currently we are working on another paper using the logic link. Later, for the software, we implement all three link functions. This is a list of parameters for the model with time effect, including mu, beta, and gamma, and tau square. The model without time effect is quite similar, just deleting gamma j from the model. Accordingly, the number of parameters is only 3. That is mu, beta, and tau square. The power calculation is again based on a wall test. This is a formula. The challenge here is to compute the variance of beta high. Based on the likelihood theory, variance of beta high can be obtained by the inverse of Fisher information matrix. I skipped the technical details. If you are interested, please refer to our paper. One thing I want to mention is that this method doesn't have a closed form formula. The likelihood function is complicated and involves integration. And the numerical method is used for the computation. So the computation is quite intensive, especially for the case with time effect, and the number of periods is large. We are now working to improve the method to reduce the computation cost. Okay, now I move to the GE method. The Hutton and Hughes method and our maximum likelihood approach only handle the cross-sectional design. The GE approach may calculate the power for both the cross-sectional design and the cohort design. Unlike the mixed effect model, the GE model needs to specify a mean model and a variance model. This slide shows the mean model using the similar notation. There is no, this is the mean model. There's no random effect in the model compared with the generalized linear mixed model. And PIJK is now not conditional on the random effect, since there's no random effect in GE model. The link function G can be identity, log, and logit. This slide shows the variance model. For binary outcome, we only need to specify the correlation matrix. For cross-sectional design, there are 2 levels of correlation, alpha 0 and alpha 1. The example here shows 3 periods and 4 individuals at each period. Alpha 0 is the within period correlation. That is the correlation between individuals from the same period. Just so here, the correlation within the same period. And alpha 1 is the inter-period correlation. That is the correlation between individuals from different periods, like this one. They are from different period, so that is the correlation is alpha 1. For Hutton and Hughes method and our maximum likelihood method, the correlation structure is a compound symmetry or exchangeable. That is, alpha 0 is equal to alpha 1. And for the closed cohort design, there is one more level of correlation, alpha 2, within individual correlation. For cohort design, the individual, recall that for cohort design, the individual from different periods are actually the same group of people. For example, Y111, Y121, and Y131 are actually repeated measurements from the same individual. And so their correlation is alpha 2. So that is alpha 2, and this is alpha 2, and this also alpha 2. And similar for outcome Y112, Y122, and Y132. And this alpha 2, alpha 2, and alpha 2. Okay, that's for the variance model. And the mean model and the variance model are connected by these generalized estimating equations. Here, Yi collects all outcome from class I. That's Yi stack all outcome into a vector. And similarly, Pi stacking all probability into a vector. And Vi here is the variance covariance matrix of Yi, and it's defined in this way. Here, Ri is the working correlation matrix as specified on the previous slide for the variance model. The GE estimator Ci can be obtained by solving these estimating equation, these generalized estimating equations, and the variance covariance matrix of Ci can be obtained by this model-based estimator, this one, and then we can calculate the variance of beta. When we have the variance of beta, we just can use the power calculation formula to get the power. Now we use PPIOD study as an example. The outcome is binary. That is unintended pregnancy and a 6 hospital and a 4 time period. K here is the number of individuals at each period from every cluster. K is 900. And the baseline prevalence is about 18%. And we consider two possible treatment effects with relative risk 0.8 and the relative risk 0.9. ICC is estimated as 0.022. This number was estimated from previous study. And we also consider 4 types of time effects. The first one is no time effects. We use the model without time effects. And for other 3, we use the model with time effects. Even though for second one, the time effect is very, very small. And the third one, the time effect is moderate. And the fourth one, the time effect is kind of large. And here, delta is the difference of the pregnancy rate for individual at the last period, but receiving control, compared with the pregnancy rate for individual at the first period receiving control. So delta is not related to intervention, only for the control. So just compare the pregnancy rate at the last period and at the first period, one individual receiving control. Now, this table shows results. We can see that our maximum likelihood method is more powerful than others, and the Hazen and Hughes method underestimates the power. When there exists time effects, the power is much smaller compared with the case without time effects. Okay, let's move to the software. Hazen and Hughes method is often inaccurate for a binary outcome. The power may be over or underestimated. To improve this approximation for binary outcome, our group proposed a conditional method using generalized linear mixed model, and Fine proposed a marginal method using generalized estimating equation. And the motivation for the software package is that this new method had not been implemented in publicly available software. And also existing software didn't have accurate power calculation for binary outcome. So we have developed user-friendly software, including a SAS macro and an R package to implement power calculations for stepped-wedge designs with both continuous and binary outcome. And in this talk, I only focus on the binary outcomes. Two statistical models can be used to account for the intra-cluster correlation in stepped-wedge designs. That's a conditional model and a marginal model. Conditional model are based on a mixed effect model, which accommodates the intra-cluster correlation where latent random effects. Marginal model describes the population average response values across cluster periods and are usually fitted with the generalized estimating equations. The difference between these two models lies on the interpretation of the regression parameters. And when the outcome is continuous, these two models are actually coincide. And when the outcome is binary and the link function is logit, and these two models are kind of different, although the difference is small. Okay, these slides summarize our maximum likelihood approach. And we consider two cases, with time effect and without time effect. And this slide summarizes the GEE approach. In the paper, Fine only considers the model with time effect, and we derive the formula for the case without time effects and implement in the software package. So we also include the model with time effect and without time effect for the GEE approach. Okay, for binary outcome, we implement both the conditional model and the marginal model. The conditional model is only available for the cross-sectional design with exchangeable variance structure. That is, alpha 0 is equal to alpha 1. And also include 3 link functions with time effect and without time effect. As I mentioned before, the computation is high, and we are now working to improve the computations. For marginal model, the software can handle the cross-sectional design and the cohort design. Also includes 3 link functions and cases with time effect and without time effect. The marginal model has closed form formula for power calculation, so it's fast compared with the conditional model. One thing I want to emphasize is that the existing software, even for the continuous outcome, doesn't support the case without time effects. So if you want to calculate the power for the case without time effects, our software is the only choice. I use the R package to show how to use our software. This is the call in R, and the K is the number of individuals at each period. And design is the design matrix for the study. I will show later how to set the design matrix. And family can be binomial for binary outcome, and Gaussian for continuous outcome. Model can be conditional and marginal. And the link function can be chosen from identity, log, and logit. The time is cross-sectional or cohort. And this mean response start is the mean response in the control group at the first period. And the mean response and 0 is the mean response in the control group at the last period. So if we set these two, mean response start and the mean response and 0 are exactly the same, then the function will use the model without time effects. And if these two are different, the function will use the model with time effect. And this mean response and 1 is the mean response in the intervention group at the last period. So the difference between these two, mean response and 1 and the mean response and 0, is just the treatment effect. And these two are generally used for continuous variable. And the type 1 error, the default value for type error is 0.05. And we also can set 3 levels of correlation. That's alpha 0, alpha 1, and alpha 2. The alpha 2 here is only for the cohort design. This table shows the arguments, options, and default value I already introduced. So now we move to the example. I use the PPI IUD as an example. And here, that is the baseline prevalence is 18.1%, and the anticipated prevalence after intervention is 16.3%. Now I use R to show how to use our method. Okay, that is R here. And the first step is to load the library, that's IWD-PWR. And if the library is not installed in R, so if not installed in R, you need to use this command to install the package into R. It's very simple, just follow the instruction. Since I already installed the package, so I skip this step. So then we load the library, and then for the design matrix, we just use this command to get the design matrix, so that the data that we can show that 6 cluster and 4 period. And for the first case, we try the case without time effect. Since the marginal is fast, so here we use the marginal model. And we use marginal model, and the type is cross-sectional, and we use the link function as logit. and that is the design matrix is data we just generate. And for these two, mean response start, that is 0.181, and this one also 0.181. So these two are exactly the same. So the function will use the model without time effect. And that is 0.163, just this number here. And the type error is 0.05, and we set alpha 0 and alpha 1 are equal both as ICC here, that ICC here. And then we can see that the power is 0.859. Now let's calculate the power for using the model with time effects. So here, we just change these arguments, just slightly decrease this number. So now this one and this one are different. So the function will use the model without time effect. So we can see that here, when there's time effect, the power is much smaller than the model without time effect. Okay, let's back to the slides. That is the command I use for the two examples. That's with time, without time effect and with time effect. Okay, conclusions. The Hutton-Hughes method is inaccurate for power calculation with binary outcomes, and the power may be over or underestimated. And two methods using mixed effect model and the generalized estimating equations can be used to calculate power of stepped-wedge designs with binary outcome. And we have developed user-friendly software, including a SAS macro and an R package to implement power calculation methods for stepped-wedge designs. And these slides collect the important paper cited in this talk. And this is the Hutton-Hughes method. And this is our maximum likelihood approach. And this is Fan's generalized estimating equation approach. And this is a software paper and is now available online. Okay, now I'm ready to take questions.
Thank you, Dr. Zhou. Very interesting talk, and we have questions. You indicated that Hussey and Hughes method is inaccurate and could give a result that's too small or too large. What is missing from their method that you included in your method that makes the difference? What is it that they've left out?
I think the reason here why Hutton-Hughes method is not accurate is that they use the approximation method. They use approximation to they use the approximation to.
Is it they use the normal approximation where they should use a t-score?
Oh, I don't think so. Oh wait, no, fine. Okay, that's the slide here. They use a normal approximation to
estimate the variance.
Yeah, the variance. Actually, they assume the variance is a constant, but it's not true for binary outcome. And for the individual in the control arm, the variance is actually the P1 times 1 minus P1. But for the individual in the intervention arm, the variance is actually P2 times 1 minus P2. They are different. So I think that is one reason here. That's what I can think about.
Okay, thank you. Now I did note on slide 11, I think, you used z-scores.
Sorry?
On slide 11, if you can go to slide 11. Yeah, you've got a z-score there, z1 minus alpha over 2.
Oh, this is not this is not J-score. This is a quantile of the standard normal. Then when we use alpha as 0.5, then this number is 1.96.
Right, right. But that is okay if you have a large number of clusters. But what if you have a small number of clusters? Should you use a t-score instead?
Yeah, that is a good question. I didn't think about it.
We have done work with group randomized trials and shown that the t-score is always accurate. Z-score is only accurate with a large number of clusters. And I suspect that the same thing applies in a step wedge.
Yeah, I think that's a good suggestion. Okay, yeah, I think, but I need to think about for the t-score. But how about the degree of freedom? How to set the degree of freedom?
Well, that was another question I was going to ask. Calculating degrees of freedom in a parallel group randomized trial is pretty straightforward. But in a step wedge group randomized trial, it can be more challenging calculating the degrees of freedom. You don't have to think about it if you're using z-scores, but you do have to think about it if you're using t-scores.
Yeah. I agree. And actually, for real study, the number of clusters is actually kind of small. Yeah, I think that is a very good question. Yeah, but currently I don't know how to answer the question, but I will think about it. I think that's a good suggestion to use the t-score instead here.
So your software supports two different approaches. One is based on mixed models. The other is based on GEE. When would you recommend the mixed model approach? When would you recommend the GEE approach?
Oh, okay. Regarding which method should be used in the study design, my suggestion is that if GEE will be used for data analysis in the analysis plan, then go with the GEE approach. And if mixed effect model will be used for data analysis, then use the maximum likelihood approach for power calculation.
All right. Is there a difference in power between these two methods, these two approaches?
Generally speaking, the generalized linear mixed model is more efficient than the GE model since the generalized linear mixed model is based on the maximum likelihood. But actually for the method here, the number of parameters used in the two methods are different. I will show that for the maximum likelihood method, that is the parameter we use. We have a mu, beta, gamma, and tau square. But for the GE method, there's no tau here. So for the GE method, there are less number of parameters. So from this point of view, the GE method should be kind of efficient than maximum likelihood method. So it's like a kind of trade-off. So we compare since we have the software, we compared some simple configuration. Sometimes the conditional method has large power and sometimes the GE method has large power. But the difference between them is very small.
Okay.
But I guess when the cluster size is large, the conditional model would have larger power, just as I showed in the result here. That's the maximum likelihood method and the GE. I think when the cluster size is large, and probably the maximum likelihood method is more efficient.
Okay. You talk about a case with time effects and a case without time effects. And many of us who have been reading the step wedge literature for a long time have understood that you should always include time effects in the analytic plan. But you're talking about including them or not including them in the sample size calculation, and I suspect that also means in the analytic plan. When would you consider not including time?
Yeah, that is a great question. Actually, this question should not be answered by statistician, and that is a question for investigator to see if there is this seasonal variation or secular trends, and how large is the time effect. But I don't think they know it well, especially at the design stage. My suggestion is that when the duration of the study is short, for example, several months or within 1 year, then there is probably no time effect. But caution is needed for the case without time effects, since the time period is highly correlated with the intervention. That means a higher probability to receive the intervention at later periods. So the time is a potential confounder when there do exist time effects. So if you design a study without time effect, but after collecting the data, you find there exists time effect, it would be a disaster, as you don't have enough power to detect the treatment effect, since you have to adjust for the time period in the data analysis.
Right. So the cautious approach might be to always include time effects.
Yeah, if you are
so
not,
that you have a large enough study to find treatment effects, even if there are time effects.
Yeah, that means if you are not sure about the time effects, so to be conservative, you may design the study with time effect. Just like what I did in the talk, you may set a very small time effect, and the cost is that you may need to enroll much more subjects in the study.
Now, the slide that we're looking at now, number 23, shows a large drop in power, even when the time effect is very small. Can you comment on that?
Oh, yeah.
Why is the small time effect creating such a big problem?
Yeah, that's because for the model without time effect, there's only 3 parameters. So for the model without time effect here, oh wait. Yeah, for the model without time effect, there's only 3 parameters. That is mu, beta, and the tau square. But for the model with time effect, that is more parameters. There are j plus 2 parameters. When the number of periods is large, and when the j is large, so the number of parameters change a lot for the model with time effect and for the model without time effect. So that's the reason why the model with time effect has quite low power, even though the time effect is very small.
Okay. And you said it's not a question for the statistician to decide whether to include the time effect. That's really a question for the investigator. I like that answer. I think that's a good answer. I'm reminded of a situation. Consider an outcome like weight, and consider a study conducted, for example, in Minnesota or Wisconsin, an upper Midwest state, and you collect your baseline data in the middle of winter, and you collect your outcome, your follow-up data in the middle of summer. I promise that there will be a substantial weight loss in the control arm, even without any intervention. And that's only 6 months. So that's an example of a study that's not very long, but where we know there's a change in the outcome as a function of calendar time in those circumstances. So that's that's something that you'd know by knowing the content area.
Yeah,
And the statistician might not know that if they haven't worked with that content before, but the investigator should know that.
yeah.
I think that's important. What impact does unequal group or cluster size have with your two methods?
Oh, yeah, that's a great question. Actually, there's some paper, and also in our paper, we also discuss this problem. The result is that the power is insensitive to the coefficient of variation of the unequal cluster size. And also, there are also some other paper in the literature also point out this point. But our paper also show that the power, actually the CV here, that is a coefficient of variation of cluster size, is kind of insensitive for the power, but the ratio of intervention to the control has much larger impact on the power when the cluster size is unequal. So I think that's a kind of interesting question, but now I don't have exact answer for this question.
But it sounds like you're suggesting that variation in cluster size isn't so much of a problem for power unless it's more variable in one arm than the other.
And unless the ratio of intervention to the control is unbalanced.
And when you say ratio, you mean the number of participants in the intervention arm is different from the number of participants in the control arm?
Yes.
Yes. Okay. Interesting. Does your calculator, the software in R, does it handle decaying correlation over time in a cohort?
Oh no. Yeah, that's the reviewer also asked the question for us, but currently we don't incorporate the decayed correlation.
Is that something you're planning to add?
Yeah, I think so. Since the method was also derived by Fan, I think we are kind of not hard for us to implement this method.
Okay. We are just about at time, so I'm going to thank you very much for your presentation and for taking a number of these questions, and I will turn things back to Dr. Moyer.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in the next 2 weeks. You'll receive an email with a link to the recording when it's available. Thank you and have a great rest of your day.